If a charged particle enters a region of space permeated by both an electric field and a magnetic field, it must navigate two distinct forces simultaneously. The combined interaction of these dual fields exerted on the particle is known as the Lorentz force. This equation establishes the mathematical rule. The total force vector is the sum of two parts. The first half is the electric component, depending on charge Q and electric field E. The second handles the magnetic component, which depends entirely on the velocity vector v. To predict a particle's trajectory, we have to treat this equation as a complete mechanical blueprint for how fields steer matter. The electric force acts linearly. It pushes or pulls straight along the field lines. The magnetic force behaves with far more geometric complexity. This equation isolates the scalar magnitude of the magnetic force. It requires the charge, Q, speed, v, and magnetic field, B. But the crucial factor is the sign of theta, the precise angle of attack between the particle's velocity and the magnetic field. If a particle moves perfectly parallel or perfectly anti-parallel to the magnetic field, theta is 0 or 180 degrees. The sign drops to 0, and the field exerts zero force. The field only exerts its maximum possible force when the particle approaches strictly perpendicular to the magnetic field lines at a full 90 degrees. Electric fields will push a particle no matter how it moves. A magnetic field's grip is entirely conditional on the geometry of the particle's approach. Calculating the strength of the magnetic force is only the first step. Predicting the direction it will push the particle requires moving into three-dimensional space. The mathematical cross product in the Lorentz equation strictly forces the resulting force vector to exist in a third, perpendicular dimension. Looking at this right-side diagram, if the velocity and magnetic field vectors lay flat on a single yellow plane, the resulting force vector must shoot squarely up or down away from it. To decode this cross-product geometry physically, physicists use the right-hand rule. By pointing your fingers in the direction of the velocity vector and sweeping them toward the magnetic field vector, your extended thumb maps the exact direction of the resulting force. Fleming's left-hand rule provides a valid alternative method, assigning velocity, field, and force to three perpendicular fingers to solve the same orthogonal relationship. Both of these physical rules come with a strict caveat. They assume the particle has a positive charge. If the particle carries a negative charge, like an electron, the math demands the resulting force vector flips exactly 180 degrees in the opposite direction. These interactions are chiral. Left and right orientation, along with the sign of the charge, dictates the resulting physics. Because the magnetic force always pushes strictly perpendicular to the particle's path, it produces a profound thermodynamic consequence. These equations set up the mathematical proof. We evaluate the dot product between the magnetic force vector and the particle's velocity vector. Since the vectors are perfectly orthogonal by definition, their dot product evaluates strictly to 0. Translated into physical reality, this means the magnetic force delivers absolute zero mechanical work to the particle. A static magnetic field acts only as a steering mechanism. It can bend the trajectory into a circle, but it cannot increase the particle's speed or alter its kinetic energy. Because this geometry is completely predictable, we use it to standardize how we measure magnetic fields themselves. This definition text establishes the Tesla, the SI unit for magnetic field strength, derived entirely from these force constraints. Exactly 1 Tesla of magnetic field exerts 1 Newton of force on a 1 Coulomb charge, moving at 1 meter per second perpendicular to the field. By tracking the rigid rules of orthogonality, we can quantify magnetic influence accurately across any scale. We can test these theoretical rules against concrete spatial configurations to build intuition. These 4 sketched cases determine force direction from velocity and magnetic fields. In case 1, a negative charge moves downward into an outward field. Applying the hand rule and flipping for negative charge, force pushes right. In case 2, a positive charge moves up into a rightward field, dictating a force pushing straight down into the plane. Case 3 features velocity pointing outward into a rightward field, forcing the particle directly upwards. Finally, case 4 introduces a negative charge moving into the plane. The geometric rules invert, yielding a force vector pulling to the left. Mapping these vectors turns abstract electromagnetic fields into highly predictable mechanical pathways. To find the true absolute Lorentz force, we have to synthesize the math, combining the linear electric push with the chiral magnetic steering. This written problem sets up a 3D vector calculation, defining the particle's charge, velocity, electric and magnetic fields. The electric component is a simple multiplication of charge by the 2J electric field vector. The magnetic component requires fully executing the cross product across the I, J, and K axes between velocity and magnetic vectors. When combined, we find the unified force vector acting on the particle. This vector math solves real engineering problems. It is the exact method early cathode ray tubes used to steer electrons and paint continuous images onto heavy glass screens. Scaling up, these identical principles allow physicists today to trap subatomic particles and steer them around a 27-kilometer ring at near the speed of light. The Lorentz force equation remains our primary bridge to translate the invisible presence of electromagnetic fields into the physical control of matter.